So the picture language seminar has a number of good talks upcoming in the future. Next week, Abby Vigverson will talk, then Rencheng Ren, David Evans, Chengkan Wan, Shun Gao, and Joost Slingerland. And today we're really happy to have Nilanjana Datta. She's professor at the University of Cambridge, had been a student at ETH and was many places, including APFL, before coming to Cambridge University. Her title is Discriminating Between Unitary Quantum Processes. And Nilanjana, we're looking forward very much to your talk.
Thank you very much. Many thanks for the invitation to give a talk in this nice seminar series. I'm just going to try and share my screen with you. Just 1 minute. Yeah, can you see the first slide?
Yes.
Okay, so 1 minute, yeah. So my talk is Discriminating Between Unitary Quantum Processes, and this work was our lockdown project, and it was done jointly.
I'd just like to say that Nilanjana has said that she'd love to have interruptions and questions during the talk. So don't be afraid, and let's be interactive if we can.
Indeed, if any of the answers are too long, then I might postpone it to the end of the talk. But yes, please feel free to interrupt. So as I was saying, this was our lockdown project, and this is work done jointly with Simon Becker, who's a PhD student in Cambridge, Ludovico Lami, who's in Ulm, and Cambyse Rouze, who was my PhD student and is now a postdoc in Munich. And this is, as you can see from the archive number, it's a pretty recent paper, which is there on the archive. Okay, so discriminating between unknown quantum objects in a finite set is a fundamental task in any experimental science. So let us talk about discriminating between the most fundamental objects in quantum mechanics, that is quantum states. So suppose you are given a quantum system A in an unknown quantum state, say rho, and you are told that rho is either the state rho1 or the state rho2 with equal probability. So the set whose elements you're wanting to distinguish between is the set S, which consists of the state rho1 or rho2 and rho2. So for example, the system A can be an electron, and therefore its Hilbert space is C2. And say the state rho1 is the 0, 0 state. By 0, I mean the upspin state, whereas rho2 is the plus plus state, which means an equal superposition of the upspin and the downspin state. And your task is to determine whether the state is rho1 or rho2. Okay, so in order to do so, in order to do this task, you perform a measurement. And since you want to distinguish between two options, you do a two outcome measurement, which I denote by this M. And say if the outcome is 1, you devise your measurement in a manner so that if the outcome is 1, you infer the state to be rho1. If your outcome is 2, you infer it to be rho2. Of course, you can make an error in your inference. And so let's look at the average probability of error in discriminating between these two states for a given measurement M. So I denote it by this symbol, PR of rho1 and rho2, and it depends on the measurement. So it's given by an expression as shown on the right-hand side. So here, this denotes the probability that you infer the state to be rho1 when it's actually rho2. And here the other way around, you infer it to be rho2 when it's actually rho1. And the factors of half appear because, as I said, the initial state is either rho1 or rho2 with equal probability. So the optimal error probability, which is given by PR of rho1, rho2, is obtained by taking an infimum of over all such possible measurements. And there is a beautiful theorem by Holevo and Hellstrom, and this theorem gives us an explicit expression of this optimal error probability. It is half 1 minus the half of the one norm distance between the two states rho1 and rho2. And here's a reminder what that means. So this quantity takes values between 0 and 2. And we are in particular interested in the value 2, because when this takes a value 2, then the error probability is 0. And that means you can perfectly distinguish or discriminate between the two states, row 1 and row 2. So row 1 minus row 2, their one norm distance, is equal to 2 if and only if row 1 is orthogonal to row 2. So for mutually orthogonal states, the error probability of discrimination is 0. And this is, of course, in accordance with what we know from quantum mechanics, that because in quantum mechanics, one can only perfectly discriminate between mutually orthogonal states. So we see that the optimal error probability is 0 if and only if the two states are mutually orthogonal. Now, what if you're given multiple, say n, identical copies of the unknown state? So now you get row tensor n. And this row tensor n is either row 1 tensor n or row 2 tensor n with equal probability. Having this multiple copies, does that help you in distinguishing between the states? So in this case, the optimal error probability, that is denoted as P error with the superscript n. So this is the optimal error probability in distinguishing between the two states when you're given n identical copies of it. So this is just what we had before, the error probability when the states row 1 and row 2 are replaced by their n-fold tensor powers. And we know the expression of this quantity by the Holligo-Hellstrom theorem that I just showed. So which is just this expression where I've replaced row 1 and row 2 by their n-fold tensor powers.
Sorry,
yeah.
This optimization, before you had an infimum over a single measurement, are you now allowing yourself to choose measurements for each time step?
No, you do a measurement, a collective measurement in general over all the n copies, because the Holligo-Hellstrom theorem is after the optimization. So if you're given any two states, yeah, the states are row 1 tensor n and row 2 tensor n, you optimize over all possible measurements, the optimal error probability is given by this expression.
Okay, thank you.
Okay, so now that is beautiful results by Nussbaum and Scholar and Audenat et al., which tells us the large n behavior of this quantity. And they showed, it follows from their results, that it decays exponentially with n, where n is the number of copies. And this constant sitting in here is called the quantum Chernoff bound. Okay, the details of it will not be relevant for us, but let me just say what that quantity is. So it is given by such an expression, minus log of the infimum of some parameter s between 0 and 1, trace row 1 to the s and row 2 to the 1 minus s. But as I said, the details of the quantity is irrelevant. Just notice that xi takes values between 0 and infinity, and it is equal to 0 when the two states are indistinguishable. Yeah, and it is equal to infinite, it is infinite when row 1 and row 2 are mutually orthogonal. So when row 1 and row 2 are mutually orthogonal, then as expected, the error probability will be equal to 0, because you know that there exists a measurement by which you can discriminate between mutually orthogonal states perfectly. But let us consider the case when xi is non-zero but finite. So then we see that we can make the error probability equal to 0 only by taking the limit n going to infinity, right? If you take limit n going to infinity on this quantity, you get 0. So in a nutshell, what do we see? That perfect discrimination of two quantum states, row 1 and row 2, which are not mutually orthogonal to each other, is only possible in the asymptotic limit of multiple copies, n going to infinity, where n is the number of copies of the state. Right. Now let's go one step further, and from the basic quantities, quantum states, let's go on to quantum processes. So our focus will be on the task of discriminating between unitary quantum processes and quantum channels. I'll explain what I mean by them, but let me just say that these involve unitary operators or unitary superoperators. Okay, so what is the motivation behind focusing on unitary operators? Now, unitary operators are the building blocks for quantum computation. You know that in the quantum circuit model for quantum computation, which is the quantum analog of the general circuit model for classical computation, logic gates are replaced by quantum logic gates, and these logic gates are all unitary operators. That's why unitary operators take a particularly significant role. And what are unitary channels? Well, there are superoperators. They act on states. So a unitary channel curly U acts on a state rho, which is a density matrix, by conjugating it with U dagger, where U is a unitary operator. So rho is a state of a quantum system, U is a unitary operator, and this curly U is a superoperator or a unitary channel. And these are, we encounter all the time in quantum mechanics and quantum information theory. So let us start with a simple example. We were talking about discriminating between states. Let us talk about discriminating between unitary operators. Let's consider a simple example. So the set whose elements you want to distinguish between are given by sigma 0, the identity operator or identity matrix, and the 3 Pauli matrices. Yeah? So these all acts on C2, or in other words, on a qubit. So these are all unitary operators on C2, and moreover, they are known to form a group. So U's are given the unitary operator as a black box, say. So this is this black box, and your task is to determine whether this capital omega is sigma 0, sigma 1, sigma 2, or sigma 3. So what do? So you prepare a state, yeah? So the state of a qubit, let's denote it by this ket psi. So this acts as your input or your probe state. And this qubit, let me denote it by A. And then you send it through the black box. What does that mean? That means the operator omega acts on psi, where omega is one of these 4, sigma 0, sigma 1, sigma 2, or sigma 3. Okay, so what are the possible output states, which is omega acting on psi? The possible output states are sigma I acting on psi, where sigma I is 0, 1, 2, or 3. Okay, however, these set of states can be easily seen to form a linearly dependent set of states. And therefore, you cannot perfectly discriminate between them. They're not mutually orthogonal. So we have to do something else. So what do? We use an extra system, an auxiliary system, which in quantum information we call an ancilla. Let's call it A prime. And we use a bipartite probe state. So what does that mean? So you have 2 qubits now, 2 systems A and A prime with isomorphic Hilbert spaces, which is C2. And you prepare a pure state psi A prime of this bipartite system. And the A system you send through the black box, and you do nothing to the other qubit. So this is the identity operator. Okay, so here by this blue line here, I just denote the output state that you get after this operation. And this is also a state of A and A prime. So it is bipartite. What is this output state? It is omega tensored identity acting on the input state, where the identity acts on the A prime bit and omega acts on the A bit. And omega is one of the 4 unitary sigma 0, sigma 1, sigma 2, and sigma 3. So this is the picture again. And now let us choose for the state psi A prime, a particular state, which is known to be an entangled state. So it cannot be written as a tensor product of pure states of the 2 qubits. So this is called a Bell state, a state of this form. So in this case, what are the possible output states? So when you take omega tensored identity acting on this phi plus, this gives you this output state. And for the 4 possible choices, I have written what the 4 possible output states are. So don't worry about their detailed expression, but what I want to point out that these 4 states are the so-called Bell states. The important thing for those who are not familiar with this is to just note that these states are mutually orthogonal. And as soon as you have a set of mutually orthogonal states, then in principle, you can always distinguish between them perfectly. So what do we do? There exists this measurement. In fact, this measurement is called the Bell measurement. You do this measurement, the details aren't necessary for us, but we know from quantum mechanics that you can distinguish between these 4 possible output states. And as a result, you can unambiguously determine whether the original black box was sigma 0, sigma 1, sigma 2, or sigma 3. So this simple example tells us something. It tells us that use of an auxiliary system or ancilla and an entangled probe state, allows perfect discrimination of the unitaries in the set. The entanglement is essential. If the states were not entangled, then such a discrimination would not have been possible. Okay. One step further. Next, consider the task of discriminating between unitary quantum channels. So you are given a unitary channel curly U as a black box, and you are told that it is either U1 or U2 with equal probability. And so this is the setup. Suppose A is a quantum system. Its underlying Hilbert space is H of A. And let us denote by D of H of A the set of quantum states of the system, by which we mean density operators. That means positive semi-definite operators of unit trace. So U1, curly U1 and curly U2, they are channels or super operators in the sense that they take states of the system A to states of the system A again. So they act on operators themselves and hence are super operators. So when curly U1 acts on rho, how does it act? It just conjugates rho with unitary operators U1 and U1 dagger, and U2 similarly with U2 dagger. So the curly denotes the channels or super operators, and the non-curly ones are the unitary operators. What is your task? I'm sure you can guess by now. You have to determine whether this unitary channel was U1 or U2. So by what we've learned from this simple example, let's bring in an extra system or ancilla as before and try to use a bipartite system of A and A primed. Okay, let us now see explain a few things. Now, since this is a channel, what has go into it is not a vector, but in general a mixed state. So what goes in here is not just a vector in a Hilbert space, but a state of this bipartite Hilbert space, so a density matrix. So in general, let us consider it to be a pure state density matrix. So it's a projection operator corresponding to the vector psi A primed. So the A goes through the black box, which is this unknown unitary channel, and the A prime is left unchanged. So it's subjected to just the identity super operator, which I write as ID. So here we get the output, which is U tensored identity acting on this state psi A prime. And remember that U is either U1 or U2. That's what we want to distinguish between. So once you've come here, you have two possible output states, right? The output state, let me call it omega 1, if the black box was the channel U1, or the output state omega 2, if the black box was U2. So right now, once we've come here, we have reduced the problem to discriminating between two states. So once again, from what we saw from the earlier slides, we do a two outcome measurement such that if the outcome is 1, we say that the state is omega 1, or in other words, the black box was U1. And if the outcome is 2, then the state is omega 2, and in other words, the black box was the channel U2. So once we are here, since we've reduced the problem to distinguishing between two states, we can apply once more the Holliver-Hellstrom theorem and look at the optimal error probability. So the optimal error probability of distinguishing between U1 and U2, the two channels, is once again, look at this part. This was just the optimal error probability by the Holliver-Hellstrom theorem in distinguishing between omega 1 and omega 2. But there is now an additional infimum. Why? Because we are at liberty to choose the input state as we want. Therefore, there is an infimum over these input bipartite states. Okay? So, but once again, the Holliver-Hellstrom helps us. So we want to be, are interested in when this quantity is equal to 0. So let me just carry over this quantity to the next slide. So this is the error probability, infimum over these bipartite input states, half, 1 minus half, omega 1 minus omega 2, the one norm distance. I have just written out the expression for omega 1 and the expression for omega 2. And remind you that this psi is actually this pure state density matrix. So let's do something trivial. Just bring the infimum in here so that it becomes a soup. Yeah. And then look at this underlined quantity. Now this quantity turns out to be a very useful measure of discrimination for these unitary channels. And this is a well-known quantity. It's called the diamond norm distance. So the diamond norm, it can be actually defined for any channels. Here I'm focusing on unitary channels. So the diamond norm distance, it's also called the completely bounded norm. So between U1 and U2 is given by the supremum, just this green quantity of U1 tensor identity acting on psi minus U2 tensor identity acting on psi. Here A and A prime have isomorphic Hilbert spaces. So this is called the diamond norm distance. Sorry, I accidentally rubbed something out. So,
sorry,
yes?
I have one more question. I'm not sure why you needed to introduce the auxiliary space, the ancillary space at this point. Because you could have just taken, right, the state you started with, send it through the channel, and then you know that it would be either U1 psi or U2 psi. Is that correct? So far, you haven't necessarily needed to use the ancillary yet?
You could have said that you send it through the channel, but you saw from that was the whole reason for that little example that I introduced. Yeah, I had introduced the example of discriminating between unitaries operators, and there I found unless you use an auxiliary system, and in that case also a bipartite state, you could not distinguish between those unitary operators.
But that's because you had 4. Now you only have 2.
Even then, yeah, in this case too, for general unitaries, for unitary channels, you would not be able to distinguish between them. So maybe unless in some special case. So I just wanted to introduce it as a natural way of distinguishing between, carrying over from the previous example for discriminating between channels. So actually, the measure of channel discrimination is given by the diamond norm, which always includes an auxiliary system.
Thank you.
You will see it'll become clearer as we go on as to why you need that auxiliary system, because in general you need entanglement to distinguish between the two different unitaries, even if it is just 2. Okay, so this is called the diamond. Hello?
Is there a similar formula for mixed state if psi is not pure?
Yeah, so the point is here, I didn't give all the details. So this is actually not the definition. The definition is a supremum over all mixed states, yeah, and with A prime, the auxiliary system of any dimension, but there is a theorem which shows that it reduces to this expression. That's a very good question, okay? But it can be shown to be equal to the optimization only over pure states with the auxiliary system having the same dimension as the initial system. So this is the measure. Just like you have trace distance between states, you have diamond norm distance between channels.
Yeah, the size of the auxiliary system, the ancilla qubits, that's going to be 1 irrespective of the mixed state?
No. The auxiliary system has dimension equal to that of the initial system, not okay. 1. Yeah. Okay. So in other words, the error probability for distinguishing between the two unitary channels, if I just look here and introduce the definition of the diamond norm, it becomes half 1 minus half of the diamond norm distance between U1 and U2. Okay. So the optimal error probability in discriminating between two unitary channels is this expression. I have just carried it over, where I want to once again remind you that this diamond norm distance is shown to be given by this expression. Okay, I had written it as a difference of two terms, U1 tensor identity acting on psi minus U2 tensor identity acting on psi, which compactly can be written like this. Okay, so this is a trace distance, right? And we know that it takes values, the unnormalized trace distance. So it takes values between 0 and 2. So as a result, the diamond norm distance also takes values between 0 and 2. Okay. And we are interested in the value 2. Why? Because the error probability of discrimination becomes equal to 0 if and only if this quantity takes the value equal to 2. So the error probability in discriminating between two unitary channels is equal to 0 if and only if the diamond norm distance is equal to 2, in which case U1 and U2 can be perfectly discriminated. Okay, so this will be very important for us, the rest of the talk. Whenever you see a diamond norm distance or a trace distance being equal to 2, that means the corresponding error probability of discrimination is 0. So henceforth, we focus on discriminating between a pair of unitary channels, but acting on infinite dimensional quantum systems. So, for example, a collection of electromagnetic modes traveling along an optical fiber. And each mode is modeled by a quantum harmonic oscillator, something we are all familiar with. So such a system is called a continuous variable quantum system, for which we use the acronym CV. And these are always one place where we can find continuous variable quantum systems occurring naturally is in quantum optics. Now, why are we interested in such systems? From the quantum computation or quantum information point of view, such systems are candidates for many protocols of quantum communication and quantum computation. Of course, the mathematics behind them is considerably harder because of the infinite dimensional setting. So let me briefly recapitulate a few things about continuous variable quantum systems. So we consider an M-mode continuous variable quantum system. So the Hilbert space is square integral functions on Rm, denoted by Hm. And let us denote by Aj dagger and Aj the creation and annihilation operators corresponding to the jth mode. And these satisfy the well-known canonical commutation relations, which you are familiar with, the CCR. Aj ak dagger is delta jk times identity. So quantum states are now trace class operators on this Hilbert space. So let us denote the Banach space of trace class operators like this. So positive semi-definite of unit trace. And a Hamiltonian of such a system is a densely defined self-adjoint operator, and its spectrum we denote by sigma h. And we can, in this talk, I will consider it to be bounded from below. In fact, we will assume by a suitable scaling that the minimum of the spectrum is equal to 0. So the ground state energy is scaled to 0, and we call such Hamiltonians to be grounded. So now, very important thing is experimentally, suppose somebody is doing a quantum optics experiment. For a continuous variable quantum system governed by a Hamiltonian H, one only has access to states rho with bounded mean energy. In other words, you cannot create infinite energy states in a lab. So you can only have access to those states rho which satisfy such an energy constraint. Trace rho H is less than or equal to E for some finite E. So this is called the energy constraint. So a natural Hamiltonian for such systems is, as you can see, the number operator. Why? Because, as we said, each mode of the electromagnetic field is modeled by a harmonic oscillator. And this is the number operator corresponding to the kth mode. So this energy constraint leads to a modified measure of discrimination for channels acting on continuous variable quantum systems. And this modified measure of discrimination is called the energy constrained diamond norm distance. Before we had the diamond norm distance, and it was Shirokov and Winter independently of each other who introduced this, and a variant of this was considered by Pirandola. So we saw what we meant by the diamond norm distance. So what is this energy constraint? Here is the definition. Let's forget about the bits in red right now. If we forget the bits in red, then it is just the diamond norm distance between U1 and U2. Remember, this was the expression for the diamond norm distance. Yeah? Psi AA prime being a bipartite state of the system and the ancilla, which is taken to be isomorphic Hilbert spaces. But now we have an H and an E. So what does that mean? So you do not take a supremum over all pure states, bipartite pure states, but only those whose reduced state obtained by taking this partial trace satisfies this energy constraint. So you fix an E, that's at some constant E, positive constant. You have an underlying Hamiltonian, and then you defined the energy constraint diamond norm. And the mathematical properties of this have been studied in detail, and one can show that it is indeed a bona fide norm. So let us draw a little picture corresponding to this quantity. So this one is what? So you see you have a psi AA primed, okay? And these are the two systems A and A prime. Nothing happens on the A prime system, so it's subject to identity. And the U1 minus U2, this superoperator acts on the A system. So this is just a pictorial representation of the quantity in the trace norm. Okay, so the thing to keep in mind is what is this? What are you computing? You're computing the trace norm of this state, which is exactly the state which comes out at the output here. And what goes into this leg? That is important to remember. This is just the state of the system A. And what is the state of the systems A? It is rho A. It is the reduced state of the system A obtained by taking the partial trace over A prime. You'll see in a minute why this picture is very helpful to visualize things.
Yeah, I have a question. So you are tying this diamond norm to a specific state, psi AA prime.
No. There is a supremum over psi AA prime outside. I am just talking about this particular quantity whose one norm we are looking at. Yeah, but we are not tying it to any state. That's the whole reason for the diamond norm. Yeah, it is only a measure dependent on the channels and not on the input states because of this optimization. Okay.
So with this energy constraint, is the maximizer still on a pure state?
The maximizer is still on a pure state. Yes, it turns out to be still on a pure state, but this is well, the maximizer. Okay, for the it can give me a second to think. Yes, it is. You're absolutely right. The maximizer is still on a pure state, but it need not be an unentangled state. It can be entangled or any possible bipartite pure state. Okay. All right. And so you see, if you take a soup over all E positive, that means effectively getting rid of the energy constraint, yeah, because trace rho A H is less than or equal to infinity, which it is, yeah. Then you just retrieve the normal diamond norm. Okay.
Sorry, I just have one small question. I find it hard to believe that this is a norm, because if I took like a Hamiltonian, that let's just say the trivial Hamiltonian, then I wouldn't be able to distinguish between U1 and U2, I think. So are we assuming something else about the Hamiltonian? Like maybe it has like...
No, the only thing we've assumed about the Hamiltonian is that what I said, that it's grounded, in the sense that its spectrum is bounded from below and the minimum of the spectrum is equal to 0. Yeah, but I can point you to my papers and also the original papers where the mathematical properties of the energy constrained diamond norms, in fact, a whole family of them, which I, with Simon Becker, generalized later on, and they are indeed satisfy all the properties of a norm. Okay, so we study in this paper discrimination of pairs of unitary channels acting on continuous variable quantum systems. So let me start with our results. So the first result, so what I'm going to do for each result is first say it in words and then state it mathematically, and hopefully at the end give a proof sketch for at least one of the results. So the first result is no entanglement is needed to discriminate between two unitary channels acting on a continuous variable quantum system. And just remember, I had purposely focused on this example before, where we saw how entanglement is essential, but for unitary channels, it is not needed. Okay, so let me say in formal terms what we mean. So you consider two unitary channels U and V, they are unitary channels acting on a continuous variable quantum system, say A. And for any state of that system A, which means U acts in this way. So the curly U, which is a unitary channel, conjugates with a unitary operator U and its conjugate, U dagger, and curly V says V rho V dagger. And let H be a particular self-adjoint operator acting on A. So it is a candidate for a Hamiltonian, for example, the number operator. Then our theorem says that the energy constrained diamond norm for a some finite E, we can explicitly calculate an expression for it. We can compute an expression for it. Okay. So how the question arises, if this is my theorem, how does that correspond to what I said in words? How does this expression tell you that no entanglement is needed to discriminate between the two unitary channels? So let me explain that. So I've just carried over the mathematical expression. Energy constrained diamond norm for these two channels is given by this expression. Okay.
The question is, you still need the ancilla qubit, right? Even though you don't need an entanglement, you still need the ancilla qubit.
Yeah. Yes. Just hold on a second, because the ancilla qubit is there in the very definition of the energy constrained diamond norm. Yeah, I'm just coming to it. So the question is, how does this above result tell us that an entangled probe state, yeah, the state of the system and the ancilla, is not needed for the discrimination task? Yeah. So let us look at the expression for this energy constrained diamond norm. I have rewritten the expression. This is what I had a couple of slides before. But let me rather focus on the figure. So the figure was this. Remember the figure of this part, psi A prime. This is the ancilla, nothing happening to it. Here's the identity. And on the A part, you act on by the super operator U minus V. And as a result, you get this output state. Yeah. Now, remember, I told you that this, in general, the psi A prime, sorry, this is somebody who had asked me this question. To be very general, yes, you can consider even mixed states. Let us consider mixed states. And rho A, which is the partial trace of this, is this reduced state, right? Even if psi A primed is a pure state, yeah, the reduced state is in general a mixed state, right? But if you look at the expression 1, see what appears here. only thing that appears here is the state of just the system, a pure state of the system. Yeah, there's nothing, the ancilla is not appearing in this expression, and you're not getting a rho A in the expression, but a pure state, psi, or psi A, if you want to call it. So in one, only a pure state of the system appears. So in other words, what is the density matrix corresponding to this pure state? So what is this rho A? This rho A is itself a pure state density matrix. It is the projection corresponding to psi. It is psi psi. Now the question is, how can you get rho A to be a pure state? That is, if psi AA primed is itself, the only way to get this to be pure is not only this itself is pure, but it is a product state. That is the only way that the reduced state can also be pure. So you see, yes, you have an inherent optimization over bipartite states, in fact, bipartite pure states, but by the result tells us that actually we can restrict this optimization to unentangled pure states, so product states. And therefore, this result tells us that for discrimination, we do not need any entanglement. So no entanglement is needed. So this result is actually generalized as a seminal result by Aharonov, Kitaev, and Nissan. And they proved this result for the finite dimensional setting. And we have now extended it to the more complicated infinite dimensional setting. Okay, second theorem, which is I find very interesting and whose theorem result I can sketch to you just through a series of pictures.
Yeah, I got another question. The ancilla system is a single qubit, or it is also a continuous mode system?
A continuous mode system. Yeah, in general. Yeah, it can be. So it is. I mean, it doesn't make sense to have. It is.
Can't define entanglement. Yeah, okay.
We're talking about continuous variable system. So in the setting of theorem 1, there exists a positive integer n such that n parallel users of u and v can be perfectly discriminated using inputs of finite energy. So what do I mean by that? So you have, say, u and v, two quantum channels, and you can't distinguish between one copy of them, say. No, even if you can't distinguish a single copy of them, there always exists some finite number, n, such that their n-fold tensor powers can be perfectly discriminated, in the sense that the energy constrained diamond norm of the n-fold tensor power is equal to 2 for some finite e. Remember, the diamond norm being equal to 2 means error probability of discrimination being equal to 0. So just a few little things here. What is Hn? It is just the n copy Hamiltonian. So it's the sum of these 8j's, where each 8j just has identity operator everywhere except on the jth location when it has h, where it has the Hamiltonian h of the system. So pictorially we have like this, that there always exists a finite number n such that you can perfectly discriminate between n parallel users of u and n parallel users of v. By parallel users, I mean n-fold tensor powers. Okay, and we found this a rather remarkable result. So in particular, as I said, that even if u and v are such that their single copy diamond norm distance is not equal to 2, by which we mean u and v, a single copy of them, cannot be perfectly discriminated, there always exists a finite n such that n-fold copy diamond norm distance is 2 and can be perfectly discriminated. Okay. Now this is in contrast to the case of state discrimination, with which I started the talk. Remember, there I showed that if you have two states, which you can't distinguish single copy wise, that means two states which are not mutually orthogonal, then even if you're given multiple copies, they can only be perfectly discriminated in the asymptotic limit. So if the two states were originally not discriminatable, then for no finite n can you perfectly discriminate them. Whereas in the case of quantum channels, we find something which is completely different. That even if they were single copy of them was not, even if we were not able to discriminate between a single copy of them, there always exists a finite n for which their n-fold powers can be perfectly discriminated. So let me just say that this theorem too is an extension of a celebrated result by Antonio Assin in 2001. He proved this thing, the fact that you can discriminate unitary channels for given a finite, for a particular finite number of them, copies of them, in the finite dimensional setting. So our result is an extension once again to continuous variable systems, or that means infinite dimensional system. Okay, so the most familiar unitary channels that we are all familiar with from quantum mechanics are those arising from the time evolution of a closed quantum system evolving under the action of a Hamiltonian. So let H and H prime be Hamiltonians governing the evolution of two such quantum systems, say A and A prime. What do I mean? Consider this scenario. Say you have two unitary channels. Yeah, this is one which we are all familiar with. This is the time evolution generated by the Hamiltonian H. I call it U sub t because it depends on the time t. And this is that of the other system, which has a Hamiltonian H prime. So then the channel is Vt, yeah, which has H prime sitting in it. And let A and A prime be, again, systems with isomorphic Hilbert spaces. And this is the way these channels act on any state rho in this Hilbert space H. Okay. So our third result, it quantifies the relative drift caused by the two different unitary dynamics generated by the Hamiltonians H and H prime respectively. So what does that mean? So if, let me state the result and then explain. So if H minus H prime, the difference between them, this operator, is in some sense small with respect to H. So in mathematical terms, if H minus H prime is relatively H bounded, that is, it satisfies such an inequality. So here alpha and beta are positive constants. And for all state psi, you have this inequality satisfied. Under this condition, what you see is that for all times and all e's, the energy constrained diamond norm satisfies such a bound. So you have a bound now on the energy constrained diamond norm of these two channels, which we encounter by just the time evolution under the Hamiltonian H or the Hamiltonian H prime. This corresponds to H and this corresponds to H prime. And you see that the bound depends on alpha, beta, the energy threshold, and T. This looks like a mathematical result, but it gives something very interesting. What does it give? It gives a novel type of quantum speed limit. So let me remind you all what one means by a quantum speed limit. What is meant by quantum speed limit? So in its initial original formulation, we can consider the following example. It was actually done for a finite dimensional system to start with. It was defined then. So consider a closed quantum system A, and let T min be the minimum time needed for the system A to evolve from a given initial state, say psi in, to a prescribed final state, or even a class of states. So, for example, you can say you have a given initial state psi in, and you want the minimum time T min needed so that after this time, you reach a state which is orthogonal to the initial state. This is one particular scenario. Then what a quantum speed limit does is it provides an estimate of this minimum time needed. That is a quantum speed limit. In the very first formulation, we found that it was Mandelstam and Tam who proved that the minimum time needed for a state, given state, to evolve to something which is orthogonal to it satisfies this bound, where delta E is the variance of the energy of the initial state psi in. Since then, there have been various other generalizations of the quantum speed limit. One example is that if you start with an initial state and you want to evolve to a state which is not only orthogonal to it, but has expected energy E, then the minimum time needed satisfies another bound like this, which is even shown to be tight. And there have been various other generalizations. Maybe you want to start with the state and go to a state at a certain angle to it, not necessarily orthogonal. Or you want to start with a mixed state and want to evolve to another mixed state, which is at a prescribed distance d from it. And you choose your favorite distance measure, for example, trace distance. It has also been studied in the setting of open quantum systems, say with bounded generators. So this was just a little digression on quantum speed limit. But what I said is what our result 3, it gives us a corollary, a novel type of quantum speed limit, by which we mean a bound on the minimum time needed for the two different dynamics. Remember, we were considering two different Hamiltonians, H and H prime. So you want to consider the two different dynamics, how it evolves a given state to a pair of states. So this is the scenario. Say you have two systems A and A prime. You prepare them both in the state psi. You let one evolve under the Hamiltonian H, the other evolves under the Hamiltonian H prime. And you want to see what is the minimum time t needed such that the distance between these evolved states is some prescribed number d. Okay? So schematically, I mean, this is really schematically represented. So this is the state psi. It evolves under one Hamiltonian and goes to phi t. It evolves under the other Hamiltonians, goes to phi t prime. And you want to find the minimum time so that they are a distance d apart from each other. And you want to find an estimate on Tmin. In other words, you want to find a lower bound on the time taken to achieve this. And what we find is our result 3 that I just stated gives us an explicit lower bound on this t. So it gives, therefore, a novel type of speed limit, which depends on this d, this e, and the alpha and beta, which appeared in the relative boundedness condition. So just to summarize, quantum speed limits in the literature are bounds on the minimum time needed for a given initial state of a quantum system to evolve to a prescribed final state or a class of final state. And the initial state may be pure or mixed, and the quantum system in question could be closed or open. Whereas our quantum speed limit pertains to either you can look upon it as two different quantum systems, or more importantly, two different unitary dynamics. So two different A and A prime evolving under H and H prime, both prepared in the state psi. And now you say, what is the minimum time needed so that the evolved state is some prescribed distance d apart? And we find an explicit bound on this. Okay. In fact, one can go one step further. You can extend it. Here we are just considering closed quantum system, two closed quantum system evolving under H and H prime. What if you consider one closed quantum system and another open quantum system? So here you have unitary dynamics ut of a closed quantum system resulting from a Hamiltonian H, and you compare it with the dynamics of an open quantum system, which is governed by a quantum dynamical semigroup denoted in this manner. Okay. So what is lambda t? Each lambda t is a quantum channel, by which we mean a linear, completely positive trace preserving map for every t greater than or equal to 0. And what's a quantum dynamical semigroup? Well, lambda at time 0 is just the identity superoperator. Lambda at time t plus s is the composition of lambda t and lambda s. So this is the semigroup property. And it also satisfies strong continuity. So if you take the limit t to 0, then lambda t rho minus rho, their trace distance is equal to 0. But of course, you can't just compare the dynamics of any closed system with any open system. That doesn't make sense. So what do? Let's consider a reasonable scenario. The scenario is this. You have a quantum system. It's governed by a Hamiltonian H. It's a closed system. So its dynamics is governed by this channel, UT, which is just the evolution operator corresponding to this Hamiltonian. Now, let's compare it with an open system. So suppose you take this system and put it in a bath, a thermal bath, for example, so that there are unavoidable interactions with its environment. So now this dynamics, this system is no longer closed, it's an open system, and its dynamics is governed by a quantum dynamical semigroup. And so at any time t, lambda t can be written as e to the TL, at least formally, where L is a generator of the dynamics and in general can be unbounded. But I need to specify something else. It's not just any possible generator. So we consider this generator to be this well-known GKLS type form. So these are after Gorini, Kosakovsky, Lindblad, and Sudarshan. So it is densely defined on an appropriate subspace of the Banach space of trace class operators. So it acts on a trace class operator in this manner. And now you will see the connection. This is the Hamiltonian part, okay? And this is the dissipative part. These operators L sub L are called Lindblad operators. So do you see that this H is the same as this H? So you're comparing a closed quantum system whose dynamics is governed by H to an open quantum system whose Hamiltonian part is the same as that of the closed quantum system. And there is an additional dissipative part. And the theorem goes like this, that if the dissipative part is again small in some sense compared to the Hamiltonian part, so there is once again this relative boundedness assumption, then for these constants and for every state psi, then you find that the energy constrained diamond norm distance with respect to that Hamiltonian, which is common to both evolutions, of course, satisfies such a relation. So you see, you're comparing unitary dynamics with quantum dynamical open system dynamics. Yeah? And we can invert this once again to find a very interesting quantum speed limit, which is what is the bound on the minimum time needed if you start with both the open and the closed quantum system to be in the same state rho. Let one evolve under the normal Schrödinger dynamics and the other under the quantum dynamical semigroup. And you want to find the minimum time needed so that this trace distance is equal to some fixed quantity d. And you get an explicit expression for it, and therefore, again, a novel type of quantum speed limit. Do I have some time for proof sketches, Professor Jaffrey?
Well, your time is almost up, but why don't you go very quickly for a few minutes and we could have a discussion.
Okay, or I could, the proof sketch is very interesting because it's just a matter of a few figures. But maybe if you want, it's probably better that I summarize and then during the question session, I give the proof sketch. Is that a better idea?
Whichever you prefer.
That's difficult to say. No. I don't know whether people are interested in, okay, let me summarize. And then if there is interest, I'll give the proof sketch, which is really just some figures and of one of the theorems. And so if you allow me to just skip ahead and I'll go to the summary slide first.
Yeah, the number of Lindbladians are finite or infinite? The cross operators for the open system.
It is of the GKLS form. Generally, it's a finite number of Lindblad operators, not an infinite number.
Yeah, I mean, GKLS is for infinite, actually. It's both. So in
yeah,
your
here in the only assumption we have is this relative boundedness condition between the, even if it's an infinite, doesn't matter as long as the relative boundedness condition is satisfied. Okay, so let me give a summary. So we studied discriminating between two unitary channels U and V acting on continuous variable quantum system A. For example, modes of an electromagnetic field traveling through an optical fiber. And the measure of discrimination was the energy constrained diamond norm, which is the natural measure of discriminating between quantum channels, but we need the energy constraint because we are in infinite dimensions, and in infinite dimensions we cannot, for continuous variable systems, you cannot ever prepare states of infinite energy, so you need the energy constraint. And what we prove, the first result, is that surprisingly entanglement is not needed for this discrimination task. And we proved in addition that even if the two channels are such that a single copy of them cannot be perfectly discriminated, there always exists a finite number n such that their n-fold tensor powers can be perfectly discriminated. And we also obtained novel quantum speed limits by considering unitary channels, UT and VT, arising from time evolution of closed quantum system, say generated by two different Hamiltonians H and H prime, but also quantum speed limits which pertain to one closed system whose unitary dynamics is UT, and an open quantum system whose dynamics is generated by a dynamics corresponds to a quantum dynamical semigroup, but such that the generator has the same Hamiltonian part as the closed quantum system. So very many thanks to you, and thanks to my co-authors. The paper's on the archive, and all relevant citations are included therein. So since I see I've just reached the hour, I think I'm going to stop there. Thank you.
Thank you very much. Thank you very much, Nilanjana, for a very interesting talk. And I'm sure there are lots of questions, but first let's applaud.
Thank you.
Bye-bye. So I could ask a question at the beginning. Can you show us a formula for a representative speed limit?
Okay. Right. I didn't write out any of the formulas, okay, but I can give you one. Give me 1 second. Okay, so for example, one of the quantum speed limit formulas will be, so it is, and you wanted to see how exactly the expression goes, right? Of the use and the, how the relative boundedness conditions come in. Probably, is that what you're interested in? You wanted to see a particular expression, yeah. So for example, we would, maybe if I write, you can see my screen, I'm sure. So let me just introduce a new slide and write an expression for it. I'm just trying to find a place to introduce a slide. Sorry. Oh, yeah. So for example, you can get that t, that is the minimum time, or you can call it t min or t, is less than equal to, or is greater than equal to root now d delta plus, I'll tell you what these quantities are, psi squared minus nu psi whole squared divided by delta squared. Now what is this? So nu psi is equal to some constant gamma. So this gamma and is a constant which appears in the relative boundedness condition. Alpha and, no, sorry, alpha and beta were the, let me write. H.
Hamiltonian bound, yeah.
Yeah, plus beta. So, so this was the situation. So remember we had two Hamiltonians H and H primed, yeah? And we were comparing the evolutions corresponding to these two. And I consider here that the relative boundedness relation reads like this. Psi H psi is less than equal to alpha psi H0 psi plus beta psi mod squared. Sorry, not writing it very well. So I'm taking the energy constraint diamond norm with respect to a fixed H0 and H minus H prime psi also satisfies, sorry, is less than equal to this relative boundedness condition of H psi plus delta psi. So this was the relative boundedness condition that I wrote. This I had called alpha and this I had called beta. Sorry, I've got using different notations now. And in fact, you can, in the particular example I gave, you can forget about this relation. So this is the relative boundedness condition. And then you get a relation of this sort where delta is what we called actually beta before. And gamma is what I'd call alpha in the rest of my talk. And so you see, this is the sort of expression you get.
And the other alpha isn't there.
The other alpha, the gamma won't be there in this particular case because this was a more general form of the theorem. When I post the slides, I will introduce a slide with an explicit expression in the PDF version so that you have that.
Are there other questions?
Yeah, so generalizing this to comparing two open systems, it's the same Hamiltonian, but connected to two different baths. That may not be too difficult, I guess, right?
We haven't done that. It's a bit difficult because what is the condition of the theorem? The condition of the theorem is a relative boundedness condition where the dissipative part is not too large corresponding in comparison to the Hamiltonian part. But now you're saying you're going to consider two different open systems. Mm-hmm. So now, what are you going to compare with what? So it's not intuitively obvious what to consider, under what constraint you would get the right result, or you would get a quantum speed limit.
Okay, so so that okay. The other generalization is that what kind of a superoperator can be treated in this method. So you use the conjugation as one example.
So this treatment was entirely about unitaries channels because it is for unitary channels. It's well, I didn't get the chance to talk about the proof, but the proof is extremely tailored to the fact that the spectrum of a unitary operator lies on a unit circle. Okay. And so even though, Arthur, you'd said that your discussions normally carry on for a few minutes.
Yes, go ahead, show us some pictures.
Can I show you some pictures? Okay, yeah, then you'll get an intuition behind why it is possible. So let me just draw some pictures. Sorry, let me go to the pictures. Okay, so I'm just going to try to convey to you the idea behind our theorem 2. So what was our theorem 2? Theorem 2 said that you have two channels, curly U and curly V. You cannot say they're just arbitrary unitary channels. In general, you can't distinguish between them. So the energy constrained diamond norm distance between U and V, so U minus V, energy constrained diamond norm, is in general not equal to 2. But the theorem says, doesn't matter, there always exists a finite n for which it will be the diamond norm distance between U tensor n and V tensor n will be equal to 2, which means that you can distinguish n-fold copies of that. Okay, so in order to see how is this possible, that originally you can't distinguish, but there is some n for which you can distinguish. So I wanted to show you some pictures which shows that. Okay, so what one can show is that one can start off by, let me start with this. I won't give you a lot of detail. So let's start off by just considering U and V, two channels. Yeah, here you can also call them U prime, V prime, just two arbitrary unitary channels, and say, when is its diamond norm distance equal to 2? So one can find that a necessary and sufficient condition for the diamond norm distance between any two unitary channels to be equal to 2 is that if 0, the origin, belongs, sorry, I used the wrong thing, belongs to this set. What is this set? This set is the set of complex numbers, psi, W, psi, where what is W? W is just U dagger V. Remember, U was a unitary operator corresponding to the channel U, and V was the unitary operator corresponding to the channel V. Okay, so a necessary and sufficient condition, I have not gone through the proof of it, I don't have the time, is that there is a particular set of complex numbers which are made of all these quantities, psi W psi, where W is U dagger V, for psi's satisfying this constraint. And what one can show that if 0 belongs to this set, then the diamond norm distance is 2. Okay. Now what one can show is that the interior of the convex hull of the spectrum of W is contained in the union of all such sets SEW as given by this expression. So if we can show that the origin, also 0, belongs to the interior of the convex hull of sigma of W, sigma is the spectrum, then what could we immediately infer? From this equation, we could infer that 0 would then belong to this set for some E, right? And that would tell us that for that E, the diamond norm distance would be equal to 2. Okay, so this would imply that the diamond norm distance would be equal to 2 for that E. So where do the pictures come? So the theorem 2 said that there exists an n such that the diamond norm distance of these n-fold tensor powers is equal to 2. So in order to prove that, this necessary and sufficient condition tells us that it suffices to prove that 0 belongs to the interior of the convex hull of sigma of the spectrum of omega tensored n, right? Because if it does, then that was a necessary and sufficient condition for the diamond norm distance to be equal to 2. Okay, so now let us see how 0 did not originally belong to the interior of the convex hull of the spectrum of W. Well, how do we know that? Because I said U and V cannot be perfectly discriminated given one copy of them. But how is it possible that this is true? 0 does not belong to the interior of the convex hull of sigma of W, but 0 does belong to the interior of the convex hull of the n-fold power of it. How does that happen? Because if that is true, then you would get, by the necessary and sufficient condition I showed, perfect discrimination would be possible because the diamond norm distance would be 2. Okay, so as I said, just a series of pictures. So let's start with the spectrum of W. W is U dagger V. U is the operator appearing in the channel curly U. V is the operator in the channel curly V. So its spectrum lies on the unit circle in the complex plane, and let W and omega and Z be the two peripheral points. Yeah, so these are the extreme points of the spectrum. Okay, so I'm skipping details. I'm just asking, is 0 in the interior of the convex hull of the spectrum? So let's draw it. No, 0 doesn't belong here, right? Because 0 is here, origin is here. So the interior of the convex hull of the spectrum does not contain 0. Good. Let's move on one more step further. Let's now consider the spectrum of W tensored 2. So twofold tensor power. So now the spectrum enlarges to Z squared and omega squared as the peripheral points. Let's again draw the interior of the convex hull of the spectrum of sigma of W tensored 2. Again, 0 is not contained in it. Okay, so we can't still distinguish between U tensored 2 and V tensored 2. Go one step further. The spectrum of threefold tensor power of W. See, the spectrum comes to Z cubed and W cubed. Draw the interior of the convex hull. Voila. You see 0 is contained in it. So U tensored 3 and V tensored 3 therefore can be perfectly discriminated. So you see, it's because even as soon as you have some opening angle, as soon as you take tensor powers, they open further and further. And to be more precise, I can say for what n you can distinguish between them. for n equal to pi over theta, where theta was the angular spread. 0 necessarily belongs to the interior of the convex hull of the spectrum of W tensor n for this n. And in this case, 0 belongs to this set for some E, and then the energy constrained diamond norm between U tensor n and V tensor n for that E is equal to 2. Thank you for your patience. So just to give you an idea.
Very good. Thank you.
Are there other questions?
I still have a question. I think I'm just misunderstanding this definition of the norm, the diamond norm. If I had, let's say I had a Hamiltonian and I had two unitary operators, and let's say that these two unitary operators were invariant on like the subspace of states with energy less than E, then wouldn't the norm between those two operators be 0 if I was taking the norm with respect to H comma E for that fixed energy E? And yet those two operators...
But are you considering unitary operators? Because this diamond norm doesn't make sense for operators. We are looking for channels, right? We are looking for unitary channels.
Oh,
yeah?
right. Taking the adjoint of those unitaries.
Okay, so what are you saying? That you have two unitary operators, U and V, say, and or unitary channels U and V, and they have some in symmetry property. And are you in continuous variable systems, or are you in?
I'm trying to write.
It doesn't matter. Sorry.
Okay. And the question was, if you look at the diamond norm distance.
Yeah, because I mean, you could imagine you take, like, you want to distinguish two unitary operators, right? But imagine that these two unitary operators act trivially on states with energy expectation less than E, right? Then that means, to me, my intuition says that that means that the norm doesn't see the difference between those two operators because they only do stuff on higher energy levels. They only mix, like they only move states around on the higher energy levels. So I would have expected that the difference, the norm between the difference of those two operators with respect to that energy E would be 0. So
the fact is, for example, I don't know whether you're acquainted with the with the attenuator channel. Do you know what the attenuator channel is? So there is a continuous variable a quantum channel. You'll see why I'm talking about this example, and it depends on a small parameter. But and so if a state goes in, for example, what's called a coherent state goes into the channel, then it is attenuated. Yeah, if it is the coherent state is alpha and the output state is say eta times alpha, where eta is the attenuation parameter. So it can be shown that if you consider the normal diamond norm distance between two attenuated channels whose parameters can be arbitrarily close or different, the diamond norm distance is always equal to 2. So in that sense, the diamond norm distance is no longer, it's too strong. And unless you put the energy constraint, it doesn't make sense. So it's therefore you have to use a suitable H for which it makes sense. Yeah. Otherwise, it could be, as you say, but for a given H, for a given E, it satisfies all the properties of a diamond norm, of a norm. So if you just drop me your email address, I can, instead of telling the others, I can easily explain to you and point you to the right part of the paper.
Okay, thank you.
So are there other questions? If not, let's thank Nilanjana again, and we look forward to seeing her paper. I hope you'll include all the additional pages in your slides that you send us.
Yeah, I will just make a non-staggered version, because then you won't have lots of slides, and I'll send it. And Yes, and if you all have any questions, further questions, just drop me an email, and I'm very happy to point you to the different
Well,
parts of the
thank you
paper.
very much again for a very nice talk.
Thank you. Bye-bye.
Bye.
Thank you.
Bye-bye.
Bye.